Okay, I don't know what just happened there. Oh, it did it again. Okay, my autofocus is doing something weird. Okay, so let me start over. Something happened with the camera, it wouldn't focus. We're going to do this real quickly again. I've got my intro video loaded. Um, you can access it by clicking there. Just click the link below the image there. I've got the notes loaded, and that's what we're about to go through. So before we start, you may want to click on these notes and download these, either PDF or a Word document. Okay, and then open them up and let's go. So we're going to start with 2.1. This is trig functions of acute angles. Acute angles, in case you've forgotten your geometry, these are just angles that are less than 90 degrees. And trig functions are for dealing, at least for now, trig functions are for dealing with right triangles, so the triangles that have a 90-degree angle. And these functions apply to any of the other angles in your triangle. Okay, so I've got a nice little picture down here for you. So I've got a right triangle, this little square down here in the bottom, which you know that's a 90-degree angle. And we've got these other two angles here. If you remember, again, your geometry type stuff, the sum of these angles, all three of them, has to be 180 degrees. We know that this angle is 90, which means these two also have to add up to 90. So, fun fact. Okay, so all of our trig functions, they're defined for a particular angle. So I've chosen this one down here in the bottom left corner. We could have chosen this one up here in the top right corner. Using this definition, however, we can't do it for this 90-degree angle. And eventually we'll get to a reason for why that is the case, but not today. So I've chosen this acute angle. Again, it's one of our angles that's less than 90 degrees. And now we've got all of these trig definitions. So the first one is sine. So the sine of our angle, this is a function here. This sine is a function of this angle, or of any angle. So if we input an angle into it, we should get some kind of output, and our output is just going to be some number determined by this. We take the side that's opposite of our angle, we divide it by the hypotenuse. So I've got it here just illustrated with pictures. So here's my angle theta. The side opposite of that is this little peace sign. I divide it by my hypotenuse, which is the smiley face, and there's my sine function. So I've got the peace sign divided by the smiley face. If I actually had numbers here, I could calculate this. A lot of times we don't want to calculate it, we just want to leave it as a fraction, maybe simplify that fraction, but otherwise leave it alone. We'll talk about that some today, we'll touch on that. So all these other definitions are similar. They relate to the sides of this triangle. So we went over sine. Cosine is the side the side adjacent to our angle divided by the hypotenuse. So in our case down here, we've got our angle theta. Adjacent to it, we've got this snowflake thing. We divide that by our hypotenuse, the smiley face, and that is our cosine of that angle. So our input, we input this angle, we get this ratio here of snowflakes to smiley faces. And so on and so forth for each of these. Tangent is the opposite side divided by your adjacent side. So in our case, the opposite side is the peace sign, and the adjacent one is the snowflake. So peace sign divided by snowflake is our tangent. Now these I left blank. You can go through and use your definitions to fill these in, and you'll notice that there is a relationship between the sine and the cosecant, the cosine and the secant, the tangent and the cotangent. You could actually see that from your definitions, but maybe when you've actually written it out, look at how sine compares to cosecant, because that's actually a really important relationship. It's one of the few things that I actually memorize from trig, because you can get away without memorizing a lot of stuff, but you do have to know these definitions. You do need to know the relationship between your 6 trig functions here. So go ahead and start memorizing this. There's some great mnemonics for it. You probably remember Sakatoa from high school, if you took trig in high school. There are also some great other ones. I looked up. I was looking up dirty trig mnemonics. This is the worst one I could come up with. It's not even dirty, but whatever. I had a friend who got through his medical school. He claimed the way he did it, you have to know a lot of terms, anatomy terms. He said all he did is he made up really vulgar acronyms. So if you haven't tried it, you should. It's a lot of fun. So there you go. One way or the other, you have to memorize these. You have to remember that sine is opposite over hypotenuse, etc., etc. Or you can remember it in terms of these great little wingdings here. Alright, so a less silly example, we've got this 30, 60, 90 right triangle. Now let's see, I've got a question here. In this 30, 60, 90 triangle, or 30, 60, 90 right triangle, this is a special type of triangle. It's super popular and important and all that stuff. Let's try to do each of these things. And I'll actually write this on the board. That's just a terrible triangle. So you can see why I print these notes out nicely. That's a terrible triangle and a terrible mark. Eek. That's a little bit. Okay, so we've got, first question we're asked is find the sine of 60 degrees. I guess I should label this, 60 degrees, 30 degrees. We've got our sides, 1, 2, square root of 3. Okay. And you can, those of you who haven't taken algebra in a while, square root of 3. Oh gosh, maybe I'll talk about this in a minute. Yeah, we'll talk about that in a minute. Okay, so let's get on with the actual question. Find the sine of 60 degrees. Let's see, the sine of 60, well that's the, sine means I take the opposite side and divide it by the hypotenuse. So in our case, my opposite side is square root of 3, my hypotenuse is 2, so that's easy enough. Sine of 30 degrees is equal to square root of 3 divided by 2. Okay, so pretty easy, right? One thing I want to mention, I'll go ahead and say this now. This is an exact representation. This is really nice because later on we're going to deal with trig functions that we do a lot more things to than just calculate one trig function of one angle. So it's really nice to be able to store that as an exact representation like this. If we actually punch this in a calculator, we get the approximate answer. If I can remember how to do this in this calculator. Square root. So I get this decimal 0.866025404 dot. So that thing just keeps on going forever. Now there's an argument to be made about significant digits and what have you, but we'll talk about that in the next section. And for the record, I don't really care too much about significant digits, but so if you ever get a problem marked wrong and you're off by a decimal place, usually I don't care. Okay. So there it is. So this again, this is the exact representation of our answer. If you can see that, it just says exact, and this is an approximate. Approximate is one of those words I spell all the time. I never know if it's right. We'll hope it is. Okay, so we could go through and do this for the rest of these. I'll do one more. Cosine of 60 degrees. that is the adjacent side over the hypotenuse. Okay. So the adjacent side is 1. That's the one right next to it. The hypotenuse is still 2. There we go. That's easy. I do want to do this one. I didn't think I wanted to, but now I do. Find the sine of 30 degrees. Because I was looking through the analytics that are provided by my math lab for the homework problems, and for whatever reason, people do okay generally with this angle. When we switch it up, it gets confusing, I guess. But so if we're finding the sine of 30 degrees, all we do is we look at our angle 30 and we take the side opposite of 30. So it's not always going to be the number over here. It's going to be whatever is opposite of your angle. So 1 is opposite of 30. That's my opposite side. My hypotenuse is going to be 2. So there we go. Now we got the sine of 30. Now this is another relationship we'll see actually in this section. This has to do with cofunctions. We don't spend a lot of time dealing with cofunctions. Maybe later on in the course. But it's kind of a cool. It's a kind of a cool feature, I guess. A good, cool thing about these functions. Sine and cosine are cofunctions, which means that when their angles add up to 90 degrees, the values, the roots are the same. So, for example, if this was, say, cosine of 20 and this was cosine of 70, sorry, if this was cosine of 20 and this was sine of 70, well, 20 and 70 add up to 90. They would also be equal like this. That's pretty cool. That's a pretty nice feature. But it should kind of make sense. Because the side opposite of this angle is the one that's adjacent to this one. And since the sine is the opposite side of 30, and the cosine is the adjacent side of 60, they both involve the same number, and they're all divided by the hypotenuse. So we'll talk more about cofunctions in a minute here. And I'll leave this last one, cosine of 30, for you to do. Okay, in this 45, 45, 90 triangle, find these two things. So just like before, we're going to look at these angles, and I asked you to find the sine of 45 degrees. And look, both of these angles are actually 45 degrees, so it doesn't matter which one you choose. You should be able to calculate this. And if you notice something, both of the legs of my triangle, they're both 1. So it doesn't matter what I choose, which angle I choose. I should always get the same value here. So let's say take the sine of 45 and pick one of our angles. I'll look at the one on top. The sine of that angle is the opposite side, which is 1, divided by our radius here, or divided by our hypotenuse, which is square root of 2. I don't know why I've got this r here, but whatever. So 1 divided by square root of 2 is our sine of 45 degrees. This is where I messed up the video last time. When I got up, it unfocused the camera. Oh gosh, it's doing it again. Oh, there we go. That time it managed to fix it. That's great. So we've got our 45-degree angles, we've got our square root of 2, our 1. So sine of 45 is 1 over square root of 2. Or if we're choosing this 45, it'd still be 1 over square root of 2. Now I'm okay with this answer. This is an exact answer. But you may see something in my math lab that talks about rationalizing the denominator. Again, that's an algebra concept, but a quick review of it. To rationalize the denominator means get this irrational number. Square root of 2 is an irrational number. It means it is a, if you write it as a decimal, you get a never-ending, non-repeating string of decimals. That's one of the definitions, I guess. Okay, so in order to rationalize this, what we mean is get this root out of the denominator somehow. I'm going to take this down here, just have some more room. In order to do that, what I'm going to do is take a different marker. What I'm going to do is I'm going to multiply this thing by 1. Put it in a special form. What I'm going to do is I'm going to multiply the denominator by the square root of 2, but also the numerator by square root of 2. But square root of 2 divided by square root of 2, and this thing I just wrote, that's 1. Anything divided by itself is 1. So what I haven't changed what I started with here. This is equal to this. This is equal to the one I started with. It's just that now I've got this term in here. And I don't know what you remember about square roots, but square root of 2 times square root of 2, it's going to end up just being 2. I'll write out this intermediate step. That's actually square root of 4. I multiply this times this. On top, 1 times square root of 2 is just square root of 2. And now I've simplified this just a little bit. On the bottom, the square root of 4 is now just a 2 with no radical sign. On top, we've got this square root of 2. So that is rationalizing a denominator. Most situations, what you're going to end up doing is just taking this radical on the bottom, moving it up top, writing as a radical down here and leaving the number down there. So another example would be like, say, so I'll do a different example. I'll come over here where there's a little more room. So let's say I had square root of 3. Oh, that's silly. You know what? I'll leave it there. This will actually be interesting. 4 square root of 3 over 5. What I'm going to end up doing when I multiply this by square root of 5, in fact, I'll write out all the steps. But I'll go ahead and write the answer, though. We're going to end up with 4 square root of 15 over 5. Trying to make this as legible as possible. I know it's a little hard to see on this video. Okay, so the way we got this, again, we can go through the same steps. I take my denominator, I multiply by that same root, square root of 5. On the bottom, 5 times 5 is the square root of 25. And up top, again, this is one of those algebra rules you got to refresh yourself on. We don't do anything with this 4 outside of the radical. That stays there. But underneath the radical, we take the 3 and we multiply it by this 5. And that gives us that 15. And then from there, the only thing left to do is simplify the square root of 25. That's 5. So again, this is one of those things that I don't really care about. I tried to remove every problem that asks you to do it, but if I miss one, that's how you do it. Not a lot to simplifying or to rationalizing those. So that's what I guess I should have written. That's what this is called. Here we're rationalizing the denominator. Again, like significant digits, this is not something I'm really concerned about. But you never know. You may find someone someday who is. All right. Now, the reason I chose these two triangles is these are probably the most important triangles in all of trig. These angles are all very special. 30, 60, 45, and really 90, although we haven't gotten there yet. They're historically very important. These are the mathematicians thousands of years ago had pretty much mastered this relationship between sides of these triangles and their ratios. And even now we try to write things as much as we can in terms of these angles so that we can simplify them easily, just because they're such well-known values. So here's a table of those values. Now I know we've only done sine and cosine, but the other ones are just as easy. I mean, you just look at your triangle to determine cosecant, secant, and cotangent. Okay. I'm not going to tell you this time. I want to see if you can determine the relationship. What is the relationship between sine and cosecant? What is the relationship between cosine and secant? What is the relationship between tangent and cotangent? So I want you to make a prediction here. I think most of you can see it just by looking at this. What is the relationship between these two? Let's see if you can figure it out. See if you can remember what that relationship is called. Okay, so this is the table. These are values you're going to need to know, and there are actually a few more. You should also know that the values for 0 degrees and 90 degrees, although those are kind of beyond the scope of our little triangle here. I want to go ahead and show you how to a nice trick to remembering these values anyway, because you do need to know all of these values. There's not a whole lot of memorizing in this class, but you'll have to know your definitions of the trig functions, and you'll have to know these exact values. So they come up over and over and over again, and if you know them, you can just spit them out and be done with it. If you don't, it's just going to be time consuming, and you won't be able to focus on what we're doing. Personally, I hate to memorize stuff. I know I have very little trig memorized, but in fact, I can show you what I have memorized. If you look in the back of your book, you've got this fantastic table, one of the only really great things about this book. But every trig book has these. You've got, I can't see it. You've got some conversions there. That's not too bad. And you've got your fundamental identities. So that's really the most important thing there. If you're really into physics, you're going to have to be really familiar with the law of cosines and stuff down here. But that's the real meat of this, to me, memorizing this little tiny box. The rest of these, I've known people who have these memorized, but I've done plenty of differential equations and partial differential equations that require that type of thing, and I just look them up. I think that's what most people do, so I'm not going to make you memorize those. Yeah, I do like this table. Oh, and there are all your graphs. Awesome. Okay, back to what we were talking about. So a trick for constructing this table, and I've got it filled out for you. I didn't fill it all out. I'm going to show you how to do this stuff. Here it is. So what I do is I just start my table at 0 and go to 90. And notice what I've written here. I've written square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. A nice simple pattern there. I'm counting up from 0, and I've got that square root written over there. But that's going to simplify in almost all these cases. Okay. Goodbye, rational denominators. Okay. So, I guess I got to write the whole table. Probably won't though. 0, 45, who needs one room? 0, 30, 45, 60, and 90. I'm definitely not going to have enough room to write all this, but I'll at least get you started. So these are our angles, and then, so these are our angles theta. And then we're going to look at first the sine of those angles. So sine of theta. So what is the sine of 0 degrees, the first one on our table? Well, According to our little chart, I just drew out the square root of 0 over 2. What is the square root of 0? What number do you multiply by itself in order to get 0? 0. Okay, and once I've done that, what is 0 divided by 2? Well, that's a terrible 0. 0 divided by 2 is again just 0. So there we go, we're at the first one. So that big mess just simplifies to 0. And after you've done this a few times, you're not going to have to write it all out. Next on our list, the sine of 30 degrees. The square root of 1 over 2. But what's the square root of 1? What number do you multiply by itself in order to get 1? Well, that's 1. I take 1, multiply it by 1, I get 1. There we go. So that one simplified nicely. 45. So I'm going to go ahead and write the rest of these. Square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. Because these next two, they're not going to simplify. What number can I multiply by itself in order to get to? There is a number, but it's an irrational number. It's like 1.7 something. Some never-ending decimal. So that one we're good on. In fact, I'll circle that. I'll circle these. That one's done. That one's done. That one's done. What about 3? I mean, you can punch that in your calculator and see, but square root of 3 is another irrational number. Square root of 4, on the other hand, is much nicer. Square root of 4 is 2. 2 divided by 2 is 1. So there we go. So there it is. We've got our first list on the table completed. So to me, this is the easiest way to deal with trig. If I've ever been away from it for a little while and these kind of slip my mind, I still remember how to get this table, and I'll write it down. And then after I use it a few times, then it starts to sink in. I remember some of these common ones like square root of 2 over 2, so on and so forth. And then you use it for a little bit, and you get back to the swing of things. So we could list these all out again for cosine, but look at our table. Cosine's the exact same thing, but we're going backwards. We're going 4, 3, 2, 1, 0. So we could write all these out again, but I know how these simplify already. Square root of 0 over 2. So down here at the bottom here, we already simplified that up here at the top. So square root of 0 over 2, which is going to go here. Look, we already went through all the work. We simplified. We got 0. So why not just write that to 0? 1/2. It's already simplified. Square root of 2 over 2. Oh, that's nice. Yeah, they're both square root of 2. Square root of 3 over 2. So I'm just doing this in reverse order. And then square root of 4 over 2, we reduce down to 1. And that's it. We've done the next one on our table. Oops. Now, in order to get this next one, we would have to talk about a relationship that we haven't gotten to, the reciprocal identities. So I'm going to leave this for now, the tangent, cotangent, and secant. We'll do this again at some point. For these, what we actually do for these other trig functions is we use these values. We use these values along with these, that one set of identities you're going to need to know in the back of the book there. These fundamental identities. That's what we're going to use to derive the rest of these. But that will happen another day. Okay. But I want to get you a feel for this table. At least you can get sine and cosine started on those, because this is the fundamental part of this table. Once you have those, these other ones are, I'm not going to give it away. I'll get there. This other thing, these cofunction identities, I already mentioned them. This is what I was talking about earlier with our angle. If the difference in of 90 in one of our angles, wow, that's a really awful way to say it. If our two angles So we got the angle we're using here and this other angle here. They have to add up to 90. If that's the case, we can they have to be equal. Now, what am I looking at this for? Now I'm trying to think how many. 90 minus 15. That's not really useful. 90 minus. How was I going to do this one? I made this one up, and I didn't think about it very well. I don't know if we can do this one. I don't know that we can find this. I was thinking of my sum identities, and this is not a sum identity. So we may not be able to do this one. We can definitely represent this, but we may not be able to actually calculate this value. I don't see how we would. So that was me not thinking this through. But actually representing that would be easy. I could represent cosine as sine pretty easily. Okay. Cosine of 15 degrees is equal to sine of 90 minus 15 degrees, which is what? 90 minus 15 is 75. So we found it in terms of sine, but that's not really useful because we don't know the sine of 75 degrees. Later on, I must have just copied this from the wrong section. Later on, we're going to deal with sum identities, and that will give us a way to actually solve this, but not in this section, not with this tool. So we can't actually calculate this, but we could have written it in terms of sine. Maybe I just left off that part of the instructions. Okay.